Okay, we are going through the topic of traffic flow parameters or traffic stream characteristics. So we have defined what do we mean by traffic stream. Okay, we have studied the two different types of traffic flow facilities we have, meaning the highways. We have studied the two types of traffic parameters, macroscopic, microscopic, and within each type there were three things which we have covered. Okay, and we also discussed in the same topics how to calculate average of daily volumes by different methods, and how to calculate the mean of speeds by different methods. Okay, so and we saw the equations, okay, between macroscopic, microscopic, and so on and so forth. Today we will start with this equation, which is the main equation of traffic flow. Okay, now keep one thing in mind. Whenever I say this equation applies to traffic flow and that equation has speed in it, it is always space mean speed. Okay, any equation of traffic flow, when it has speed in it, it is space mean speed. Okay, what is the other mean speed? Time speed. Okay, good. Now this equation says V equals S into D. V is rate of flow. V is rate of flow. S is speed. Which is speed? Space means. And D is density. Okay? V is rate of flow. S is speed. Space means speed. And D is density. Clear? Okay? So this equation says if you know speed and density, you can know the flow, rate of flow. Okay? Clear? Okay. Now there are couple of things we should remember before we use this equation. First thing is that speed, I said space means speed, right? So this is for the entire section. Space means speed is for the entire section. And density, what are the units of density?
In terms of traffic flow?
In terms of traffic flow, yes.
Vehicle per hour per minute.
No. Vehicles per what?
Per feet.
Vehicle per feet?
Mile.
Per mile, yes. Okay, vehicle per mile, right? So speed is for the whole section. Space means speed, right? It's for the whole section. And density is also per mile. So it's not a point. This equation is not applying to a point. It's applying to the whole section, because speed is for the section and density is also for the whole mile, for the whole section. Clear? Clear? But so that means rate of flow is also, if two things are for the whole section, the third thing is also for the whole section. Clear? Okay? But to make this thing happen on the road, it will not happen automatically. Okay, that you put a speed and you put density and you get the rate of flow for the whole section. It will not happen automatically. You have to apply something. Okay, so why the flow can change? For example, let's say there is an entry point here. This is my section, let's say, and there is an entry point. Okay, so some people will enter from here, right? When they will enter, the flow will change. Got it? Okay? So even if the speed and density doesn't change, the flow is not the same. We know that. Okay? So to apply this equation, the section should remain uniform. No entry, no exit. No change. Okay? This equation only applies when the flow remains, when the section remains uniform. Okay, no changes in the section. Even if you don't allow entry and exit, but you change the number of lanes. Okay, so everybody was in 2 lanes. Now you made it into 1 lane. Okay, so now they will come closer to each other, right? From 2 lanes they will go to 1 lane, right? Okay, that means the flow is not the same. They are going slowly now. They are slower. Okay, so no, that's why I'm saying no changes in the section. This equation applies when there are no changes in the section. Okay, so when you try to calculate rate of flow, first of all define the boundaries of your section. Okay, and those boundaries should be encompassing a section which is uniform. They should be enclosing a section which is uniform, no changes. Clear? Okay. Everybody? Okay. So I said we have two conditions to meet for this. The first condition is section should be uniform. The second condition is the flow should be stable. What is stable flow? When the flow is continuous. When the flow is continuous, when we don't have a Q. Q makes the flow unstable. Okay, Q makes the flow unstable. Okay, because when there is a Q, what happens? You come and you have to stop. Okay, and then you will move, and then you will stop again. This is unstable, right? This is unstable. Clear? Okay. Any problem? So there are two conditions for this equation. The first one is the section should be uniform. The second one is the flow should be stable. Clear? Okay. If you meet these two conditions, then flow rate can be calculated from speed and density. Okay. Then two very simple questions. A freeway lane has SMS. SMS is what? Space. Speed is given and density is given. They are asking for rate of flow. What will I do? Multiply that. Okay. Second one, speed is given, rate of flow is given. They are asking for density. I will divide. Okay. Clear? Any problem? You can do it, right? Okay. Or you think you can do it? You think you can do it, right? Yes. Confidence matters, right?
Yes,
Okay. These three graphs show the relationship between the macroscopic parameters. Okay. They define traffic flow. Okay. Or they are a simplified way to look at traffic flow. Simplified, why simplified? I will come to it. But I will start with the easiest one. We have discussed it earlier. Okay, the one between density and speed. Okay, when density is very high, that means everybody is very close to each other. Okay, when they are very close to each other, their speed will be low. Clear? Okay, and the other way around as well. When density becomes low, now you have more space, so you will go faster. Clear? Density increases, speed. Density decreases, speed increases, right? Okay, and the other way. Clear? Okay, any problem with that? Okay. Then we have this one, which is between flow and density. Okay, we start from here. So you see, flow is almost zero, density is almost zero. Okay, so when more vehicles approach the road, so density will increase, and when these vehicles will move, the flow will also increase, right? Okay, clear or not? Sure. Okay, so more vehicles approaching the road and nothing is stopping them, so they are moving. Okay, clear? Until they reach this value. Okay, now what is maximum here? No, capacity means what? Maximum what? Flow. Got it? Capacity means what? Maximum flow. Okay, clear? Yes, say yes. Okay, so capacity means maximum flow. And you can see nothing is zero here. Keep this in mind. nothing becomes 0. It is the top point, okay, where we have some values. Okay, so now the road is designed for the vehicles to do what? To drive, right? For the vehicles to move, okay? But they, if they are not, there may be many vehicles on the road, but they are not moving. They are just stuck. So we will not call it the capacity of the road because there are 2,000 vehicles on the road, but nobody is moving. Okay? Capacity is how many are moving. Okay? That is the flow. Okay? Capacity is how many can move. Okay? Capacity is how many can move, which is that number at the top. Okay? When you reach capacity, after that, there are more vehicles which are now approaching the road. The number of vehicles which are approaching the road has now still or is still increasing. Okay, but the capacity cannot increase. There is a certain number after which it will not go up, which is that number. From that number onwards, it will not go up. So what these extra vehicles will do, they will start to form a traffic jam queue. Okay, clear? So when traffic jam happens, we said what people start to, now they have to stop and move slowly and so on. So the flow is now doing what? The flow is decreasing, right? It is decreasing because now there is a queue. Okay, so you can see density is increasing, meaning more vehicles on the road, but these vehicles are not moving, they are just forming a queue. Okay, and they will keep on forming a queue until they reach where? Until they reach the jam density. What do we mean by jam density?
Stuck. Completely stuck.
Completely stuck. Okay, the whole, you see what happens? Queue starts and then it gets longer, right? It gets longer. Okay, it keeps on getting longer, that means the flow keeps on getting lesser and lesser. Okay, until a time comes when the whole segment is jammed. Okay, that is the point of jam density. Clear? Everybody else clear? So starts from here when everybody was approaching and moving continuously until you reach the peak, which is the capacity. After capacity, more vehicles approach, they form a queue, and the queue reduces the flow, and the queue keeps on getting longer and longer, the flow keeps on getting lesser and lesser. Okay, until you reach this point where the queue has completely occupied the whole section. Okay, so the flow is almost now 0. Okay, you have a question? No? Okay. Now we have a graph between speed and flow. We start from here. Here. Okay. The speed is maximum. Okay. Now you come to this graph, you will see speed is maximum here, right? This is the maximum speed. When density is what? Minimum or 0. Okay. And when density is 0, the flow is also no vehicles on the road, right? And no vehicles on the road. So your speed will be maximum, but your flow is minimum. Okay. When the flow increases, more vehicles come on the road, they are moving, but they are also slowing down. Okay. So you see flow increases, the speed decreases. Until we reach, again, what point is this? Capacity. Okay. And we said after capacity, what happens? What happens after capacity? Jam or Q. Okay. So now you see the Q is decreasing the flow. Okay. So up till here it was capacity, the flow increased. It reached the top point. Now there is a Q, so the flow will decrease. And then it will reach here where the flow is 0 and speed is also 0. Now this is the jam. Okay, this is the jam. Clear? Any questions? Okay. I already explained jam density. The whole section is blocked. Capacity is maximum what? Flow. Okay. We have critical speed and critical density as well. Okay. So critical density, now you see this is critical density. So when I have critical density on the x-axis, I have what on the y-axis? Capacity. Okay. So critical density is the value of density when we reach capacity on the flow. Okay. When flow reaches capacity, density at that point is critical density. Okay. And similarly, we have critical speed. Okay. Again, you can see when the speed reaches critical, the flow reaches capacity. Clear? Okay. So critical density is that density where the flow is maximum capacity. Critical speed is that speed when the flow is maximum capacity. Okay. In all these graphs, you see that they have plotted the graph solid line and dotted line. Okay. Solid line is called as what? It's written there. Stable flow, right? Okay. Meaning what? It's before capacity or after?
Before.
Okay. Because the flow is continuous, no stopping. After, they are calling as what? Forced flow. Unstable. Clear? Any questions? Okay. Yeah. I told you this is a simplified version. Those graphs are simplified versions of traffic flow patterns just to understand what happens, generally what happens. Okay, what should happen. But this graphs, which is now adopted for the real analysis of the highways, you will use it and you will draw it as well, is the one which applies to modern highways or modern drivers. Okay, so this is between speed and flow. Speed on the y-axis, flow on the x-axis. Okay, and you can see region 1. In region 1, the flow is increasing or not? Increasing, right? X-axis increasing. Is the speed decreasing? No. Okay, this is what they call is because of the aggressive nature of you guys, modern drivers. Okay, and past that stage. Okay, so what is happening? Flow is increasing, so the spacing is getting less. Okay, but the drivers have seen too many movies, Fast and Furious and so on. Okay, so they are not reducing this. They think we can still go on. Those
Animal genes. Animal genes.
I'll give you the name, you can watch it later on. Don't watch it. Okay. So, you get the point, huh? You may not have seen the movie, but you do that, right? So, close and fast movement. This is region 1. Okay? When then a stage comes, when you get to the real world now. Out of the movies, get to the real world now. It's too close now. Okay? I already smashed 2 cars, this is my 3rd one, I cannot do it. Something like this. Okay? So, now you get into region 2. Now you are too close, now you feel I have to reduce my speed. Region 2. You see the flow is increasing, the speed is going down. Clear? Okay? Then you reach point number 2, not region 2. Point number 2. You see point number 2? Okay? What is point number 2? Capacity. Okay? So after capacity we said what happens? Stop, queue, jam. Okay? So you can see the speed is, this is the one where they are called, this is the region which they are calling it as queue discharge. So the flow is not normal now, it's not stable, it is a queue. Okay? So the speed is reducing now. Okay? And the flow is also reducing because of the queue. Okay? But now you can see the amount of change in speed. It's not a smooth curve going downwards, it's a dip. Okay? From 2 to 3, it's a sudden dip. Okay? So it reaches capacity, here till here it is constant, then it gradually decreases up to point 2. After point 2, the Q is started, so there is a sudden dip. Okay? Okay, so from 2 to 3, it goes down.
So this is where they suddenly stop, right?
Yes. Okay? Because at point 2, the Q has just started. So maybe there is 1 or 2 vehicles in the queue. I don't see the queue. Huh? Got it? I don't see the queue. So I am still coming at full speed. When I suddenly know, no, this vehicle is stopped now. I have to stop. This is that point. Okay? When you reach this point, then the queue has become longer. So drivers now can see it. That there are 10 vehicles now which are waiting. So they are coming even slowly now. Okay? So this is from this point onwards, they start to reduce their speed from the beginning. Okay? So now you can see the speeds are much lower and they are gradually decreasing, not suddenly. Okay? So here constant, here gradual decrease, here sudden decrease, and here again gradual decrease. Clear? Okay? Now this graph is between what? Speed and flow. Okay? But I showed you a graph between speed and density as well, right? So if speed changes, density will also change. And there was a graph between flow and density as well, right?
Yes.
So if flow changes, density changes. So all 3 graphs will change. Okay? So those 3 graphs which I showed you, they are simplified versions. For the modern graph, I am just showing you one example. But that also means the other 2 graphs will also change. Okay? And they do change. Okay? But we are not going into that detail. Okay? Because this is enough for us to move forward in this course. Okay, then we have the field of traffic flow theory. This is the field in which all equations related to traffic flow are included. Okay, all traffic flow theory is a set of equations. What do you call guys called? Kanun, huh? So all the traffic flow kanun are part of traffic flow theory. Clear? Okay. So this was given by my childhood friend Bruce Greencheese. Okay. In 1930 we used to play together. He's very serious. She's believing me. Yes. So we used to play together. Then he made the equations. I am teaching them. Okay. We made a pact. He has passed away. I am continuing the legacy. Yes. Okay. So he started, obviously he was my friend, he was not. Okay. So he started with a straight line.
He's still alive?
Huh?
He's still alive?
No. No, he's not alive. Huh? Fortunately, how can I can say anything about it, right? Huh? You never know, huh? If he was alive, somebody would go on Facebook or Instagram and start searching it. You would tell him, Dr. Uneb was saying this thing about it. Okay, so good for me. Okay, so he started with a straight line. I told you, he was not smart, he was my friend. I can say this, right? So he started with the equation of a straight line. Okay, what's the equation of a straight line? Y equals what?
X.
Huh?
X.
Y equals x is a straight line. Yeah, y equals x is a straight line as well. But this is like even beyond the standard of Bruce Greencheese and mine. Y equals what? Straight line. Tell me.
Mx plus c.
Mx plus b. Mx plus c. No b, c, no problem. Okay, but mx plus something, right? Okay. So he said between speed and density I have a straight line. Equals meaning y equals to mx plus b. Okay. What is my y? Speed. So speed equals to mx plus b. Speed equals to mx plus b. What is my x? Density. So speed equals to m density plus b. Okay? It was y equals to mx plus b, right? Y equals to m x plus b. Okay? Clear? What is my b? B was the y-intercept, right? If I plot the graph, I can know the y-intercept. Okay? The maximum value of y. Okay or not?
What's his speed?
Huh?
What's his speed?
You know the equation of a straight line.
Yeah.
Y equals mx plus
B.
b, right? So b is a y-intercept. Okay, when x becomes 0, the maximum value of y, that is b. Okay, so if I plot this graph, then this is my b, right? This is my y-intercept, the maximum value of y. Okay, and what was m? M was the
So,
slope. Now you can see the slope is what?
decrease.
Decreasing, right? The slope is negative. Slope is negative. Okay, so y equals this minus slope into density, right? Okay, now what is slope? Y upon x. Slope is what? Y upon
Yes.
x. What is my y? And what is my x? Clear? Now you look at this graph. This value is 65. This value is 110. Okay, so I have the graph, I have the values now. Now let me write the equation. Y y equals, what was it? Mx plus b, right? Okay, so b was this value, right? Okay, y equals b, y minus negative slope. Okay, and what is this? 65 upon 10?
The maximum values.
Slope. Okay, y upon x. Y 65, x 110. Clear? Okay. So y equals to b, the y-intercept, minus slope into x. Okay? Okay? Sure? Everybody clear? Okay. So from this equation I have 65 here, 65 here. You can take it out, this is the final equation. Okay? This is the initial equation, this is the final equation. Any problem? Okay. Now in this equation we had the maximum value of density. We call it general density. We have the maximum value of speed. We call it free flow speed. Got it? Any questions? Okay. So from the straight line, I got the equation for speed and density. Okay. This equation, right? Okay. And before that, I showed you this equation. Flow equals speed into density. So now I have two equations. Okay. This equation was already there, and this is the one which we got from the straight line. Okay. Now in this equation, I will replace S from here. So S equals to what? No. S equals to V upon D. S equals to V upon D. So S will be replaced with V upon D. So D will go on the other side. This is the final equation. Okay? Okay? Clear? Okay. So I got the equation between rate of flow and density now. Now I'll go back to this equation. In this equation there was S and D, right? Here I replaced S. Now I'll go here. Now I replace D. What is D? V over S. Okay. Okay. Equation of the straight line. Replace D with V over S. Okay. Clear? Any problem? Clear? Okay. So then you open the bracket, solve the ratios, and this is your final equation. Clear or not? Yes. Okay. So I have now 4 equations. You say your counting is wrong. No, I have 4 which I can use. Okay, this one between speed and density, this one between flow and density, this one between flow and speed. 4 equations. Okay, clear? Now you can see this is the equation of a curve, right? This is the equation of a curve. When you reach the maximum point of the curve, and remember this curve is for what? Rate of flow. Okay, and the maximum rate of flow is called as what? Capacity. Okay, so when this equation reaches maximum, I get capacity. When this equation reaches maximum, I get capacity. Okay, now if I go here, this is the maximum point, right? What is the slope here? 0. Okay, so when I reach the maximum point, the slope becomes what?
Capacity.
Slope becomes slope.
Yeah.
Slope becomes
0.
0.
Yeah.
Okay, got it? You're just saying it.
No.
You believe it.
Yes. Of
Have
course.
faith in it.
Confidence. is
Very
the key.
good. No, have faith now. You have confidence when you are presenting. Okay. When I am teaching, have faith.
Sure.
Got it?
Yes.
You know the difference?
Yes.
Okay. I will ask you.
Okay, no problem.
How many marks?
What?
About
Guess
that?
what? Huh?
Why only for him? Only for him.
We have something.
You are not the chromatic.
Huh?
Not the chromatic.
No. Okay. So the slope becomes 0. Okay. So I need the equation, the slope of this equation. Okay. Slope of the equation, you have to take the derivative. Okay. What is the derivative of this equation? 65d, 65. 0.59 d square will become 2 into 0.5 d. Okay. And at the maximum point, this should be equal to 0. Okay. So if you put this whole thing equal to 0, then d equals to 55. Okay. Clear? Huh? There's another practice question. You will do this. Okay. Later on. Okay. But is the procedure clear or not?
Yes.
Okay. Now we come here. Again, this is the equation of a curve. Okay. And the curve is for rate of flow. When the equation reaches maximum, I reach capacity, right? Okay, and at capacity the slope should become 0. So I will take the derivative and put it equal to 0. Okay, clear? You're not happy, huh? Clear or not?
Yes.
Any questions? Sure. No. So you put this equal to 0 and you get the value of speed. This is your speed now. Okay, clear? Now, the slope became 0 when I reached the maximum point, right? So this is the speed at the maximum point. This is the speed at the maximum flow. Okay? And
Which
we
is
call
before
it
capacity,
critical
right?
speed.
It's before capacity, right?
At capacity.
Oh.
Okay? This is the speed at capacity. Maximum flow is what? Capacity. Okay? Slope becomes 0 when? At capacity. Clear? Okay? This whole thing is happening at capacity. Okay? Slope becomes 0 at capacity, and this is the d value at capacity because I got it from here. Okay? Same thing here. The slope becomes 0 at capacity, and this is the speed I got at capacity because I got it from here. Okay? So this one is called as critical speed, and this one is called as critical density. Okay? Okay? Why I am calling it critical? Because it is at capacity. Same thing here. Why I am calling it critical? Because it is at capacity. Clear? Okay. So flow reaches maximum, density reaches this much. Flow reaches maximum, the speed reaches this much. Okay? Clear? Now, if I put the value of density over here, this value of density over here, the flow should be maximum, right? Okay? So if somebody asks you for maximum flow, you can put this value of density over here and calculate it. Okay? This will give you maximum flow, maximum capacity. Okay? And if somebody asks you, okay, give me maximum flow but use this equation. So now you will put the speed over here. Okay? Clear? Okay? If somebody says no, use both of them together, then I have this equation. Okay? So I'll take density from here, speed from here, and I will get the capacity. Okay? In any case, the capacity should be around this much. You can check it. Okay? Either put the speed over here, or put density over here, or put both of them over here. You should get the same answer. Okay? Any questions? No? Okay. Okay, this is another question. Okay, in this question, they changed the first equation which we developed from the straight line. Okay, this was our first equation, right?
Yes.
So now it is not this, it is this one. Okay, and we already have another equation which is this is constant, this doesn't change, never. Okay, rate of flow equals to speed into density. It's always like this. Okay, so nobody has to drive it again. Clear? So this is a new equation and this is the old one. Okay. Now what is the first part? They are saying calculate free flow speed and calculate jam density. Okay. What was free flow speed? Maximum. What was free flow speed on the graph? Which point is free flow speed?
65.
65, right? That value. So when you are at free flow speed, your density is how much?
0.
0. Okay? Clear? And where is jam density? When you reach jam density, your speed is what? 0. Okay, so at free flow speed, density is 0. At jam density, speed is 0. Okay, so now we are going to use it over here. So I want free flow speed. I put what? Density as 0. Okay, I put density as 0. Okay, I will get the free flow speed. Free flow speed is maximum speed. When do you have maximum speed? When density is 0. Density 0 means what? No vehicles. No vehicles, your speed will be maximum, right? Right? Okay. So I'll put density as 0, I'll get a speed, which should be this much. Okay. For jam density, what should be 0? S should be 0. It's a jam, right? It's a jam. Okay. So that means no speed. Right? It's completely jammed, so speed is 0. So I'll put a speed 0, I'll get density, which should be clear. Okay. Any problem? No? Okay. These two steps are repetition of what I did here. Same. Okay. But instead of this equation, you will use the equation which is given. All the steps will remain the same. This is part B and this is part C. Okay. So you will repeat this whole part in this question using this equation. Okay, the equation of straight line has changed now. Clear? Okay. Any questions? Okay. Last thing we will do today is discuss about interrupted flow. Okay. The main difference between interrupted flow and uninterrupted flow was intersections. Whatever we have discussed up till now, it will not work on intersections. Though the equations and graphs do not work on intersections. Okay? Because on intersection, you may have to stop, not because of a cube. You may have to stop because of a signal or a pedestrian crossing. Okay? So somebody is crossing, you have to stop, right? Okay? So this is something external, though the equations do not consider that. They are for flow in the same highway. Okay? So though the equations and graphs do not work on intersections. Clear? Clear? Because on intersection you stop or start because of something external, not on your road, not on your side. Clear? Okay. Now what happens on intersections? A group of vehicles cross together. Signal becomes green, they go together. Okay? Or the roundabout is empty, they go together. Okay? Nobody coming from the other side, they go together, right? Or they are coming from different sides but they enter together. Maybe I was going straight and somebody took the right turn. Now we will enter together, right? We will enter the other side together. Okay? These group of vehicles which enter together, they are called as platoons. Okay? What is a platoon? A group of vehicles which enters a segment together without any break, one after the other. Okay? This is called as a platoon. A platoon is a group of vehicles which enters a road segment together. Okay? Clear? Now this platoon will move normally. Okay? Until it reaches the next intersection. Agreed? Until the next interruption comes, this flow will be normal, right? Like everybody is moving, okay? You don't have anything external blocking you, right? When the next intersection comes, they may have to stop, or some of them may have to stop because of somebody crossing or because of the signal, right? Okay? So until they reach the next intersection, I can apply my equation and graphs on them. Okay? So you have a group of vehicles, they are moving. You want to calculate their density, speed, capacity, whatever. You can use those equations, no problem. But when this group reaches the intersection or comes close to the intersection, you stop your equations. You stop your calculation. Clear? Okay? Why? Because on intersection we have, you stop. If it is clear, you will go, otherwise you will keep waiting and so on. Clear? Okay. But because of this thing, we cannot use those equations on the intersections. Clear? Any questions? Okay. Sorry, I had to go faster because we started late. Okay. So, but you should do the practice problem.